Welcome back, physics fans. Here we are, and we're going to talk about force graphs here. But before we start talking about force graphs, a force time graph or a force distance graph, displacement graph, let's take a look at other graphs that we have done already. Way back when, in kinematics, we've done velocity time graphs and acceleration time graphs. And the slope of this velocity time graph was the rise, the velocity over the run, which is the time, so that was the acceleration. Okay, and that would give us an acceleration, whatever. But one of the things that we were able to determine here, we were also able to get the area under the graph. The area under this graph, so from that time frame to another time frame here, let's just shade this in here. The area represented by that green color that I'm filling in here represented what? The area underneath it represented the change in displacement. Why is that? Because when we multiplied the area, and to get an area of, let's say, a box, we get the height and the length. To get it, we go height times length. So get this area, we go v times t, and if it was a constant velocity, then we would just get the velocity times time, and you can see that velocity times time is displacement from our constant velocity formula. V equals d over t, or rearranging it, d is equal to v times t. So when we figured it out in kinematics, in physics 11, we took this area of this triangle and added it to the area of that box, and that was the displacement. So when we added up both the green and the yellow area, we'd get the total displacement for the trip. So the area underneath it was the velocity times the time. And the area underneath the acceleration time graph, if you didn't do it, you should have. The area underneath that is the change in velocity. The change in velocity is the acceleration times the time. And one of the things we didn't achieve and didn't work on was what happens if there's changing acceleration, because we never did that. But if there's changing acceleration, we could still get the change in velocity. And that's important. We could still get the change in velocity. Okay, so where does that leave us now? Well, if we have a force time graph and we calculate the area underneath it, what would that give us? Well, that would give us the area. What's force times time? So the area under a force time graph gives us, what's force times time? That's impulse. That's impulse. It's the change in momentum. We never did graph it, but you could graph as a ball hits a wall and then it starts bouncing back. As it gets squishy and then starts unsquishing, the force becomes less, holding it together. That would be its change in momentum. The force is increasing over time. And then, okay, good. That's a good thing to note. So if I ever gave you a force time graph, you could calculate what the impulse was. If I gave you the mass of the ball, of the object, we know that would be mass times the change. You could calculate the change in velocity knowing from this graph and the mass of the object. Really cool stuff. Force distance graph. What does this give us? We had to calculate the area of this little triangle here and then add it to that little box, and then also calculate the area of this blue box What would that give us? Think about it, folks. If I took this area and say this was 10 and this was 15 and this was 40, that would be a total area of 65. But what would that represent? 65 what? Okay, well, what is force times distance? That is the work. That's the change in work, how much work you put into it as you push it over a distance. So if I gave you a force distance graph, especially when the force is changing, because you couldn't use this if the force was changing from the formula, but the area under a force distance graph is the work. So when could you use that? Well, you can use that in this formula. The kinetic energy initial plus the potential energy initial plus the work is equal to the kinetic energy final plus the potential energy final plus the heat energy, right? The conservation of energy. And if I don't tell you the work, but I give you this, you could calculate the work. The 65 would go in there, and it would be 65 joules. And which is incredible because what happens if it's not a constant force? You couldn't just go force times distance. You'd have to graph it and take the area underneath it. Incredible. Okay, try this next question. Actually, it's a quiz on the Moodle. Go ahead and try it.